Welcome to the 16th lecture in mathematical finance. All right, so currently our mathematical goal, or the goal we have, is the pricing of hedging of American options. And for this, we developed some martingale theory. And at the end of last lecture, we came back to our optimal stopping problem, which we need to solve in order to understand the pricing and hedging of American options. So let us consider for the moment a general stochastic process, which is assumed to be, of course, adapted to the underlying filtration. And we want that this is an integral process. So this means at every time, the absolute value of the process at y at time t is finite. So this is our given stochastic process. And now we consider the following optimal stopping problem. So we want to find the stopping time, which is, okay, tau is the stopping time. And so we want to maximize the expected value of the process stopped at time tau. And this is what we want to do. We want to maximize among all those stopping times which are bounded by our terminal time t. And so recall a stopping time by its definition could take the value infinity, but here we want to exclude this. And then, well, what is the solution? So our aim is looking for stopping time. Let's call it tau star, which is stopping time, as I said, and of course should fulfill also the condition that it is finite. In this case, it means less or equal than t, such that if I stop the process y at this stopping time tau star, it tends the supremum, so it's a solution to this maximization problem among all stopping times which are less or equal than t. So this tau star is then also called the solution to this optimal stopping problem. And to be consistent with the lecture notes, let me give this the number 5.3. All right. So can we solve this problem? The approach we want to take is an approach by martingale techniques, unsurprisingly, because this is why we developed the martingale theory in the last one lecture. And the way to approach this is to construct a super martingale which stops at the right time, will spit out the solution we want to have. So this brings us to our first definition for today, which is definition 5.11. And this is the definition of a Null envelope. So we define the following stochastic process. Let's call it Z. And well, how do we define it? So we have here an underlying or given process y. So we define it by a backward procedure. So we start at the terminal time and say, well, at the terminal time, my process Z should be equal to y. Okay. And now I can iteratively define what I z t is, so small t here. So this should be, or is defined as the maximum of the process y and the conditional expectation of z t plus 1, projected to the filtration at time t. So that's for t being 1 up to time t minus 1. Well, this is well defined by this iteration because I know the terminal time, and then I can define it step by step backwards until I get to time 0. This process is then called the Snell envelope of y. And even if I did not make it explicit here, it's a Snell envelope with respect to the measure p, right? Because the expected value here is taken with respect to the measure p. And I mean, I'm not labeling here making the dependence with respect to p explicit in the definition of z, but in the case of American option, you will see we want, of course, use somehow the martingale measures as a reference and not the underlying measure p. But for the general theory, this does not make any difference. All right, so this is we call a Snell envelope. Okay, and now the first step, we want to understand, why this process helps us to solve the optimal stopping problem 5.3. So let us start studying this Snell envelope process. This is what we do in the first, in the next proposition. Like, position 5.12. Okay. The Snell. So this is z t. So this is the Snell envelope as we just defined it of y t. So the process y is the smallest super martingale such that y is always less or equal than z. Right. So, just to remark it here or emphasize it here, so we haven't assumed any martingale property of y. So y is just a general adapted and integral process. And what we do now is we construct here a new process, the Snell envelope z, which is a super martingale, and it dominates at each time t the given process y. Okay, so let's prove this. Okay, so what do we have to do? Well, so we have to prove several properties. So we have to show that it's a super martingale. We have to show that it dominates y, and we have to show that it's the smallest one. Okay. So if you look at the process, well, it's easy to see that this is an adapted process, right? Because y is z is just the supremum of two adaptive processes. And it's easy to see it's the maximum of two integral processes, so it's integral again. So the only thing we need to really check here, and this is also simple, is that it has the supermartingale property. So first, this is y definition. Well, we have, I mean, that we get. So what do we see? Well, what's the definition here? Z at time t is the maximum of y and the conditional expectation of zt plus 1 conditioned on ft. So this is obviously, the maximum is obviously bigger than, well, if I take just one element. So that's ft plus 1. So this is bigger than the conditional expectation of zt plus 1 conditioned on ft. So this implies immediately that we have that is a supermartingale. We have here the right direction, the inequality to see that it's supermartingale. And well, here we also see that we can estimate it from below by y. Right? Instead of taking the second ingredients here of the maximum, we take the first one, and this is what we have here. So it's indeed, it's a supermartingale dominating the process y. Okay. So what we now need to show is that it's the smallest one. So this is the left. So let's assume there exists a supermartingale z tilde with the same properties. So it's also supermartingale dominating the given process y at time t. And what we want to show is that this new process z is always bigger than the Snell envelope z. So the given the new process, the new supermartingale z tilde is always bigger than the Snell envelope z. Okay. How can we do this? Well, let's start with a backward. Let's perform a backward induction. So well, why do you want to do a backward induction? Because if we look at time capital T, and well, if we look at the terminal time capital T, well, we know that the tilde at time t, well, it dominates yt, because it's a supermartingale dominating y, the process y. And well, we know that by our construction of the Snell envelope z, this is identical to y. Okay, so the terminal time, these z, so the Snell envelope is indeed the smallest supermartingale with the property dominating y. And now let's go backwards. So let's assume they exist time and t in, right? So let's assume we have a time where z is indeed bigger than y, than this Null envelope. Right, okay, this time exists by our induction, the first induction step here. And now we want to show if we have this, then it's also true for time t minus 1. Okay. So since this here is a super martingale, what do we get? Well, then the tilde minus 1 is, this is the super martingale property, is greater or equal than the expected value of z at time t projected to the filtration at time t minus 1. This is the super martingale here. And now at time t, we have this, by assumption, already the right inequality. So we can estimate this from below by the conditional expectation of z now, instead of z tilde, projected to the filtration at time t minus 1. Okay. Right. And now, well, what does it mean? Well, the z tilde is dominating y, so this is also bigger than y at time t minus 1. And well, by this inequality, I can take this with the maximum, because that tilde at time t minus 1 is also bigger than the expected value of z at time conditioned on the filtration at time t minus 1. Well, and now what do we see here? This is nothing else than the definition of z at time t minus 1. So we are done. And this shows us that this Null envelope z is indeed the smallest super martingale with the property of dominating the process y. Right. Okay. But we need to have some further properties before coming back to the optimal stopping problem. So let's keep studying this Snell envelope process. This is we do in the next lemma. So let us okay, so how can we construct from this Null envelope actually our what will turn out to be optimal stopping time? Okay, let us define the following time tau star. So what we do is it's supposed to be by definition the first time. So t is running through our index set such that this is better. So this is the first time this Snell envelope z is equal to the process y. Okay. Okay. What can we say about this process? Well, this time, random time here. So first, as we see in a minute, it's less or equal than the terminal time t. It's a stopping time. Okay. And if we consider the stop process, it's a martingale. Yeah. That's good because this means tau tilde is a possible admissible stopping time, in the sense admissible in the sense it's really a bounded stopping time, as we are considering in our optimal stopping problem. Okay, why is this true? Okay, first thing, we want to show that the stopping time, let me call it already tau stopping time. So that this tau star is less or equal than t. Well, certainly, since at the terminal time, we know that the Snell envelope by its definition is equal to yt. Just to show you the definition once more. Right. So this is what you should keep in mind for today. Right? This is the definition of our Snell envelope. So at the terminal time, we definitely will stop because yz is by definition, yt is equal to yzt. So the Snell envelope at the terminal time is equal to the given process y at time t. Okay, so this is simple. Now we need to verify that this is indeed a stopping time. Okay. We need to check, well, what's the visual stopping time? So we need to check that if we consider the event that tau star is less or equal than t, this is supposed to be ft measurable for all t and our index at t. Okay, let's do this. Well, what do we have? If I want to know that this event is in ft, this is equivalent to saying that tau star is strictly bigger than t. Well, this is the complement of the event that tau star is less or equal than t is in ft. Right? The property of the sigma algebra, an event is in f if and only if the complement is in ft here. All right. Okay. It is sufficient to check that tau star being bigger than t is in the sigma algebra ft. Okay, so let's do this. So we know, again, by the properties of the Snell envelope, so I know that my Snell envelope dominates my given process y. So how can we use that this is so how can we decompose this event here that tau star is strictly bigger than t into events where we know that they are ft measurable. Well, what is this? So tau star is bigger than, so tau star is the first time the process z, which stays above the process y, hits y, right? So this is, so what does it mean? So if y at tau star is strictly bigger than t, this means at time 0, z is strictly bigger than y. And at time 1, this is strictly bigger than 0. This is z is strictly bigger than y. And then we do this up to time t, where it also be the case that z is strictly bigger than y. Well, now these are adapted processes, so each event is obviously an ft. Where we used that y and z are adapted processes. Okay. Okay, so we have now checked that it's stopping time, so tau star is the stopping time, and it's less or equal than t. And now the final claim I had here is that the stop process is a martingale, while the unstop process, or the process without the stopping with respect to tau star, is only a super martingale. And this was the content of the last, right? So we know already that this null envelope is always super martingale, and now I claim if I stop it with respect to tau star, this is a martingale. Okay. So last to show that stop with respect to tau star, that I consider the stop process, is a martingale. Okay. Well, what we already know, our theory we developed last time is that this here is the super martingale. Why? Well, we know that z without this stopping is a super martingale. And what we have seen last time, that the property of super martingale, submartingale, martingale is preserved if we consider the stop process. Yeah. So this is good because, well, this means the stop process is already adapted and integrable. So we only need to check that it has the martingale property here. So to check, so if I consider the conditional expectation of the process z at time t plus 1 and now stop with respect to tau star, conditioned on the filtration at time t, well, this should be nothing else than z at time t minimum tau star. Y without 0. Okay. Yeah. Okay. So this is what we have to check now. How can we see this? So There. For t, so what do we consider? T has to be so if I need to study, and this is what we have to study, if I pull the right hand side on the left hand side, I want to understand what this is. So I consider the process at time of this null envelope at time t plus 1 minimum tau star minus this null envelope at time t minimum tau star. Well, this is the same. So if I consider this now, so I multiply it with the indicator function that tau star is strictly bigger than t. Because if this is not the case, this is here 0 anyway, so I can set the right hand side to 0. But if this is the case, well, then the minimum here is attended by at time t plus 1, and here, of course, at time t. Okay. Okay. And now, well, what we also observe is, well, if I consider the second summand here, so that if I consider the indicator function that tau star is strictly bigger than t multiplied with zt, well, if this is the case, by the definition of the Null envelope, I know that this is that t plus 1, because otherwise, if it would be y, I would have stopped, because tau star, the minimal time, the first time the process y hits the process z hits y, sorry. So I know that this is the same. Right, and of course I shouldn't forget the indicator function. All right. So what do I get here? If I plug this and put this in together, everything together. So the difference of z at time t plus 1 minimum tau star minus z at time t minimum tau star is nothing else than here this indicator function of tau star being bigger than t, and then multiplied with the difference of t z at time t plus 1 minus, now I use the second identity, so I can write here the conditional expectation of that t plus 1 conditioned on ft. Okay. And now I take the conditional expectation. So if I take the conditional expectation of this here, minus, and I condition it, of course, on ft, because, well, this is what we want to understand. Well, what is this? Well, okay, this is the same. Here I'm just copy pasting the line above just by taking the conditional expectation with respect to the filtration at time ft. Okay, so that's is not too hard, and now I forgot the conditional expectation. So that's what I have. All right. What is good now is that I know that this here is ft measurable, so I can pull it out. Here we are. So I'm left with the conditional expectation of z at time t plus 1 minus the conditional expectation of that t plus 1 conditional on ft, and all this is, I don't need the brackets here, on ft, right? And now I use the tower property, and yeah. So by the power property, well, this is again ft measurable. I don't need to use the tower property. I can also just use the measurability of this object. So this is ft measurable, so I can pull it out. No, it's the tower property is better. So, right, so use the linearity. So you have this. Right. So this is the first summand now. And the second one is, well, you take twice the conditional expectation with respect to ft. So this is what I said at first, the tower property to reduce it to 1 filtration. And well, what do you see here is that I forgot a bracket and that this is just 0. So everything is 0 as I claimed. And so this means this, the stop process, so the stop Snell envelope, this Snell envelope as a stop process with respect to tau star is indeed martingale. Cool. That's, I think, all I wanted to prove here. So we're done. Okay. And now finally, I'm ready to show you that this tau star is indeed the solution to our optimal stopping problem. And actually the Snell envelope also gives you the maximum value, which the maximal expected value you can achieve by optimizing among all stopping times, which are bounded by t. Okay, for change, let's go back to black. So theorem 514. So what do we have here? So the stopping time tau star. Wait, just to solve. So this is the, okay, let me write once the definition again. So this is the stopping time as we just have defined it. So the first hitting time of Z hitting the given process Y solves the stopping problem. So this is the first problem I wrote down. This is 5.3 in the lecture notes, but well, so what does it mean here? Just to, so if I stop the process Y with respect to the stopping time tau star, the expected value of it is equal to the supremum among all stopping times which are bounded by t. And then I consider the expected value of Y stopped with these among this set of stopping times. And I know even more. So the expected value here of y stopped at time tau star is equal to my Null envelope at time 0. Right? So this Null envelope gives me the optimal stopping time for this stopping problem, and it even tells me what is the value I can achieve. Okay. So why is this actually something you would expect? I mean, why is it reasonable? So what you do is you have your process y, you define your Snell envelope, and you keep basically playing as long as your Snell envelope is a martingale. Because as long as it's a fair game, you keep playing. And the moment where it hit this time, the stopping time tau star, your process turns into a super martingale, which is an unfair game for you, or a game which is not in favor for you. So this is the moment you decide to stop playing. So you play as long as it's a fair game. The moment it becomes an unfair game, you stop. And this maximizes your payoff given here by the conditional expectation of y stopped at time tau star. Right? This is, I mean, if you think about y as being the payoff of American option, what you do is you keep the American option as long as you basically in the regime of a fair game, and the moment it becomes an unfair game for you, so the game where you lose, I mean, in expectation start losing, you stop. All right. So let me prove this before coming back really to the American options. So first, this is the last lemma we have done. So we'll have a 513. So the stop process here is a martingale, right? So this is, I mean, I just formulate mathematically what I just explained. It's a martingale. So that at time 0 is equal to, well, z at time tau star minimum 0, right? Yeah, I mean, the minimum with 0 is always 0. So this is constant, so I can also take the condition, the expected value of this. But now this is a martingale, so the expectation stays constant, doesn't matter what time I pick. So I can swap the 0 to capital T. And now by the definition of tau star, this is nothing else than y at time tau star. Okay, so this is actually the second claim. Net here in the claim that the expected value of z at time tau star is equal to z0. And now, let us take a stopping time. No, this should be a stopping time. Such that it's bounded by t, right? So this is one of the set among which I want to maximize. Then we have our proposition we just had before. So this is the first one we proved today. What you call it? That. So the process, the Snell envelope is a super martingale. So what does it tell us? So if I consider process Z, and now also this Snell, so I stopped it now with this respect to this stopping time. So any stopping time, so any arbitrary stopping time which is bounded by t. Well, Z at time, so the Snell envelope times 0 is equal to, well, if I stop with respect to this and take the minimum as 0, so this is nothing else than, so same calculation actually, right? But now I'm only a super martingale, so I have here not the equality anymore, but an inequality. So this is that max minimum t. And as my stopping time tau is bounded by capital T, well, this is nothing else. I mean, and its Snell envelope is dominating the given process Y, so it dominates right? So Z is always bigger than Y, and tau is smaller than T, so I get here YT. Right? And this is the second claim. So if I take here now the supreme over all, I get the second statement. All right. Let me remark this. Z dominates and tau plus equal T. All right. Okay. So far so good. So we understand now how to solve this optimal stopping problem here. And this is what we want to understand in order to price American options. So that's what we are doing now. So let's come to, let's go back to the case of American option. Okay. So this brings us to section 5.3, pricing and hedging of American option in complete markets. All right. Where is? So what is our market? So we wanted to consider finite. So we want to have access to our fundamental theorem at asset pricings. We want that it's arbitrage free, right? Otherwise, pricing and hedging makes no sense. Otherwise, not reasonable. And we want that it's complete. This is just for simplicity. We will discuss next week, also with the incomplete case, but here we're not going through all the proofs. Financial market. So as usual, this is B&S, so we have a risk-free asset and a risky asset. So why this is my B. So this is a deterministic process. Well, and to make my life easier, I normalize the risk-free asset to be normalized to 1 at time 0. And this is a stochastic process which models the risky price evolution of the future prices. Right. Okay, this is our standard setting. And now what? This is in the right. So we consider a complete market. So what do we know? There exists a unique equivalent martingale measure Q. So this is the measure here in our set M star. My first and second fundamental theorem of asset pricing. Right. So this is our fundamental theorem. So we know there exists exactly one equivalent martingale measure. Okay. That's good. Wait. And we wanted to consider an American option. An American option. So this is our process, a non-negative process. So mathematically speaking, is just an adapted non-negative process. And this process the process Z models the payoff if I stop at time t. So Zt is the payoff at time t if I stop at time t. With, as usual, the discounted counterpart of it is Z divided by our risk-free asset. So the risk-free one is always assumed to be strictly positive. Okay. And I already made a claim. We haven't proven it. So recall this is actually the first theorem of this section. So 5.5. So we claimed, and up to now it's still a claim because we haven't proven it yet. The arbitrage for a price of our American option C is given by given by this optimal stopping problem. So if I allow myself to stop among all stopping times, which are bounded by capital T, and now I want to stop this everything under the martingale measure Q, and I stop the discounted price process, the discounted counterpart of the American option. Right? And actually, there was the second claim of this purpose. The theorem was that this is actually the unique arbitrage-free price. But these are two steps, right? So first, we need to show that it's indeed the arbitrage. It's an arbitrage-free price for the American option C, and then we want to show that it's unique. So let's start with the existence. So this is what we had, and so let's show that. So let's first show that this is indeed true, and this means we find the price of an American options. Oh, okay, of an American option, right? And the hedging problem is then, so why? First pricing, then hedging. While for European options in a complete market, we did it like in one go. Here we split it up into two tasks. So now we know how to, well, so you see here let's label it like in the lecture notes with 5.4. So this is an optimal stopping problem, and we know now how to solve an optimal stopping problem this time. So let us define this null envelope. And now I want to emphasize that this null envelope is here. We have the optimization problem with respect to our quadratic measure Q. So let me also indicate this in the notion of the Z. And it should be this null envelope of the discounted payoff of the American option, so that Z tilde with respect to Q. So actually, you know what this is now, so you can look up the definition as we have done earlier today. So this is at the terminal time, this null envelope that Q is supposed to be the same as Y. That's the Y. Sorry, okay. It should be Y, but Y is now my discounted price process here. And in this kind discounted payoff, the American option. And at the time t, well, we do our definition by a backward recursion. So at time t, it's the maximum of Z tilde at time t and the conditional expectation under Q, and here you see why I want to call it with respect to Q, of Z time t plus 1 condition on ft. Okay, cool. So this is just spelling out the definition we made earlier today in our current setting. Okay. And now let me put together what we know then. So again, let us define this. Well, what is our optimal stopping time? Well, we just learned that this is supposed to be the infimum of t in our index at t, such that our Snell envelope hits the first time that t. Okay. So this is a solution to our optimal stopping problem as we have just learned. So this means then an arbitrage-free price and yeah, you might already guess it, right? So this is, we know what this object here is in terms of the Snell envelope. So the arbitrage-free price of the American option C is given by, so let me denote this A, so P of American of C is defined as the Snell envelope with respect to Q at time 0. And this is the same as the value, the maximum value of our optimal stopping problem. So that's right. Okay. Yeah, and we know even more. I mean, we have learned a lot about the optimal stopping, solving this optimal stopping problem. So what else do we know? Well, we also know that tau star here is our, I mean, there might be more than one, and well, this is what you understand hopefully now in the, I mean, in the next exercise sheets. So the optimal execution strategy here is given by the stopping time tau star. So what does it mean? Well, it's a solution to the optimal stopping problem, right? So if I want to maximize my payoff among the martingale measure, this maximum is attended with respect to tau star. So this is stopping time equal, and then so this is the best choice. I want to stop the discounted payoff of the American option with respect to Q. Right. Okay, let us do the proof now, which is actually not very hard because well, we did already all the preparations. So proof. Let me change the color for a moment. Proof. All right. So, okay, this is just putting together what we have learned today. So we call our last proposition theorem 5.14. So let's go back. Here we are. This means this tau star is the solution to the optimal stopping problem, and the Snell envelope at time 0 is the expected value of the optimal stopping problem stopped at this stopping time tau star. Okay, so let me write this down. So I know if I stop the discounted payoff till the z with respect to show it to you at time tau star, this is equal to the supremum over all stopping times, which are supposed to be less or equal than t, and then the supremum among all the stopped discounted problem. And now what was also included in this theorem 5.14, well, this is nothing else than the Snell envelope with respect to Q at time 0. Okay. So this is the second part. So this tau star is an optimal exercise strategy. So what remains is it remains to check that this a PA of C defined as our Snell envelope at time 0 is an arbitrage-free price. Price for the American option, right? We want to use our definition. We had a different definition for European option, so let me emphasize here the arbitrage-free price for the American option. Okay, so we need to check two things. First one is that the price is not too expensive for the buyer. So first thing, just to observe here. Well, if I consider my stopping time tau star, so the first property of being an arbitrage price for American option was that the price is not too, as I said, too expensive for the buyer. So I want to find a stopping time which tells me if I stop like this, the price is, what I'm willing to pay. And if I take now my stopping time tau star, and I consider the European, so the arbitrage-free price of the stopped American option. So if I stop the American option with respect to tau star, it's a European option, right? Because this is just a non-negative random variable, which was a European option. So I have there an arbitrage-free price, which was denoted here by this the set of all arbitrage-free prices by this capital P. And then C should be less or equal than pi. Sorry. Right. Okay. So why is this the case? Well, this is, we have a complete market. This is at some point we want to use that we have no complete market. So indeed, since BT ST is an arbitrage free and complete market, follows that, this pi here is nothing else. There's only one. So with the European option that stopped at time tau star, there's exactly one price, and this price is given by the expected value under the martingale measure Q of the discounted, expected value of Z stopped at that time tau star. Right? So this is the European price, which means Well, we know that A and C, right? The American price, I mean, we just defined it as here we are. Let's use this equality here. So by star, this is nothing else than Q of that. And this is nothing else than P. Maybe we should. Yeah, so this is. Okay, so this is right. So as a buyer, I'm willing to price this price P AC because I stop with respect. I can stop with respect to or exercise the American option with respect to the stopping time tau star, and then I realize gains which tell me okay, I'm willing to pay the price PAC. And the second thing I want to observe, which is a check, is, I mean, so the second property of an American option means there exists no stopping time with is supposed to be, well, this should be an exercise strategy, so I assume that it's less than capital T. Such that, well, I can stop my American option in a way that I get more money, strictly more money than more value than I paid for it for all possible prices of the European option. So P pi prime is an arbitrage free price of the European option. The stop with respect to the stopping time tau prime. Right? And again, I mean, this set here is nothing else than, I mean, this is a single element. So I have here a complete market. Again, note, we have here a complete market. So P prime is nothing else than the expected value under Q of the discounted payoff stopped at time tau prime. And this means there indeed exists no stopping time. Well, it has to be an exercise strategy, so tau prime has to be less or equal than T, such that the American price, which we just defined as supremum of all stopping times which are less or equal than T, of the expected value under Q of C prime times T, well, this cannot be strictly bigger than being then the expected value under Q of C stopped at time prime, right? Because this is this tau prime here is allowed stopping time, which is so would this be the case? This contradicts the supremum. So this is why we have really no such stopping time, which does this job here. All right, and this means this is the price PA of C we just defined is indeed an arbitrage-free price. Right. All right. So just a remark, which has the number of 416 in the lecture notes, but this is not so important. So this is the lemma we just proved is here 515. So the last one we just did describes the perspective perspective of the buyer of the American option. Why is this, I mean, clear? So in this lemma, if we go back, I mean, tells you basically the price the buyer is willing to pay for the American option, because the buyer can find an optimal exercise strategy which achieves the payoff. Right. So I can find the exercise strategy which ensures I get the realization or realize payoff by stopping with respect to this tau star here, which tells me the money I spent for the American option was worth it. Yeah, but what we haven't, I mean, investigated yet is, and this brings us from the next lecture to the hedging problem, is there's some seller willing to sell for the price. But first we need to finish this pricing problem, and the second thing I claimed in the proposition so I want now to finish the proof of theorem 5.5, right? So as I well recall, so the, where is it? Here we are. So what I claim here is the American price of the American option, an arbitrage-free price, is given by this identity here. And so my last lemma showed me that this is true. And now I want to add here that this is actually the unique price. Right. So this is the missing step. So because this is what I also claimed in proposition theorem 5.5 is that there's an arbitrage-free American price given by this formula, and this is actually the only one we can choose. Right. So existence is it's now easy. My lemma 5.5 PA of C given or defined as the supremum of all stopping times, which are less or equal than T. I take the expectation of all the stop discounted American options is arbitrage free price. Right. So this is what we already have done. And as I said, the missing step is that we also want to verify that this is indeed the only arbitrage-free price which exists on a complete market. Right? In the incomplete case, as we will discuss next week, there might be, of course, again, a set of arbitrage-free prices, but in the complete one, and this is unique. Well, how do we show that a price is unique? Well, we assume there's a second one, and then we show that they are equal. So suppose exists another arbitrage free price. Let's call it P tilde A of C. Okay. Okay. So the definition, right? So I just want to use the definition now to verify, well, there cannot be another one. The definition of arbitrage free price. And this is, if you want to check it out again, by 4. And here I used actually the first part. So what do we know here? They exist. Stopping time tau. Let's call it tau tilde to be consistent with our notion of price here. P tilde. With this smaller or equal than t, right? So it's an exercise strategy such that the price A tilde of the American option C is less or equal than P for some P in the set of arbitrage-free prices of the European option now C stopped at time tau tilde. Okay. But now, again, since the market here is complete, and of course arbitrage free, well, we know that this set of arbitrage free prices of Z stopped at time tilde tau is just given by the singleton of as given by the conditional the expectation of under Q, so our unique martingale measure of this claim here, right? Okay. So what does it mean? Well, if I look at the price of the American option, which here the another price, so the price tau tilde. Well, I know it's less or equal than the expectation of the discounted. And this is what I showed, claimed here, or it has to be true in order that this is an arbitrage-free price. And this is, of course, less or equal than if I take the supremum over all possible stopping times, which are less or equal than t. Right, one element is always less than the supremum overall. And this is now actually by definition our arbitrage free price PA. of C. Right? Okay, so we already know that any other price of the arbitrage-free price of the American option has to be less or equal than the one we just already, claimed as an showed that it's an arbitrage-free price, which is P of A. Okay, so now we want to show the inverse equality. So again, so this is, let's make it like this. And this here is the other one. Again, by the definition of arbitrage-free price. And now you won't be surprised that I use the second property of an arbitrage-free price. Well, what do we know? Oh, what can we conclude? Well, there exists no stopping time which leads to a strictly bigger value of the American option. So what I know is that if I consider the American one, so if I consider the supremum of all stopping times which are less or equal than t, well, this here has to be less or equal than p tilde a of c, right? And this is, of course, just here the definition, right? Because we know that it cannot be a stopping time which gives me really a strictly bigger payoff value for the corresponding European one than this one. So I know the supremum has to be less or equal than this arbitrage-free price p tilde a of c. And this is the definition. The supremum is the definition of our arbitrage-free prices. So we also have the other inequality. So let me conclude. Let me conclude in black. Hence, the price, the p tilde, has to be equal to p. And this is what we wanted to show. So there's really, in a complete market, only one arbitrage-free price for the American option. All right, let me stop here for today. And next time we will talk about the hedging of an American option, which is more the seller's perspective, right? So well, the buyer is willing to pay the price, but we are still not sure if there's a seller who's willing to sell the American option for this price. And this is depends on, okay, can I hedge myself against the risk of the exposure I might have, the obligations I have by selling this American option. All right, thank you.